Hello, everyone. It's my great pleasure to introduce our speaker today, Professor Anoop Sarkar. Anoop is a professor at Simon Fraser University at British Columbia, Canada. His main research is focused on developing machine learning algorithms for natural language processing. And in particular, he has made great contributions to statistical machine translation, text summarization, and also decipherment of ancient documents. He has been the co-chair of a NACL conference in the last year, and also he has received numerous awards for his research and teaching achievements. And today he will be talking about his very exciting recent work on simultaneous speech translation. Thank you.
Thank you. Thank you so much for having me here. I'm very excited to introduce this topic to you. It's an interesting topic. I hope to convince you it has a lot of potential for future research. We've only just scratched the surface in some of our recent work. So these are my two collaborators on this talk. Mariam is my PhD student, and Hassan is my master's student. They both so if you like this talk, it's thanks to them. If you hate this talk, it's probably my fault. And both Mariam and Hassan are finishing up, and they're both looking for positions. So if you like this work, then you should contact me, and hopefully, you might want to employ one of these people. So I'm going to talk about simultaneous translation. And the context is speech-to-speech translation. So there's been a few speech-to-speech translation systems developed. I'll just mention some of the more commonly known ones. So this is the one developed at Karlsruhe. It's a lecture translator, Alex Weibel's group. There's the NICT speech translator, which comes from this team, NICT in Japan. And of course, probably most of you have either used or heard of Skype translator, which is so incorporates machine translation into Skype. So this obviously has sort of lots of potential social benefits. Like I would like my daughter to be able to talk to her two different grandmas, right? And even though my mom speaks English, my daughter doesn't really understand her English. So maybe even a translator for that would be good. And on the other side, her other grandma doesn't speak a lot of English. So it would be great if we were able to enable this kind of technology. So the sort of standard way that speech-to-speech translation works is it's not simultaneous. I would like to emphasize this task of simultaneous translation. So for example, there was this famous demo by Rick Rashid where he was talking and he was being translated into Chinese speech as he was talking in English. And this is true even of Skype translator. You have to kind of pause to wait and catch up so that the other person can hear the translated version, right? So this is kind of unnatural. That's not how we talk. It's also sort of not how, so there's a field called conference interpretation. This is like the field of human interpreters. They're called interpreters, right? Which is confusing from a computer science perspective. So that's why we say simultaneous translation, because when we think of interpreters, we think of Python and not. So I'm going to use the term simultaneous translation, but human interpreters have been doing this. So you have somebody speaking in a language like Spanish, and then there are different human interpreters producing an output in the different languages and you kind of have an earphone, and you hear the translator speaking, and you're looking at the person talking in a different language. And the person talking is just talking normally, because he or she is not aware of the translation happening at all, right? It's not it's not happening sort of, there's no user interface where that person who's talking is seeing the translation happen. So there's a very good book about the history of human interpreters. It's this one called From Paris to Nuremberg. According to this book, and I guess I believe this particular author, it's sort of modern conference interpretation got started in the aftermath of World War I and the Paris Peace Conference. What is interesting is almost right away, there were some concerns about how to evaluate this. Like how, is it a good interpreter or a bad interpreter? In this particular setting, there were many people who were bilingual, who were actually able to evaluate the interpreters talking. But there was always this notion of trying to minimize the delay and the translation quality. So, I mean, it's amazing what these people do. So interpreters are very highly trained. An interpreter who has 1 year of training is very, very different from an interpreter who has 15 years of training. I had the opportunity to talk to some interpreters, and the impression I got was they were kind of like professional athletes. They have to keep practicing. So if the person sort of stops interpreting for a few weeks, they can't really get back into it. They have to sort of do this gymnastics of trying to keep up with the conversation. They're hearing one channel in their ears, and then they're producing the translation simultaneously, right? So just to give you, there's a good exercise. So even if you don't speak another language, one exercise you can do is, as I'm talking, try to paraphrase what I'm saying in your mind. As I'm saying stuff, you try to paraphrase it, and you try to keep up with what I'm saying, and in your mind, you're trying to paraphrase it. It's very, very difficult. You have to be very concentrated to do it. And this is, so you can stop doing it. One interesting thing is that machines actually might be better at this than humans because they don't have the same kind of memory requirements. Humans have certain drawbacks in terms of how fast they can do things and how much memory they can consume when they're doing translation. So, of course, we're far away from human performance now, but there's some reason to believe that we might actually do better at that than humans. So here's an example, which I stole from Graham Newbeck, and this is a Japanese source sentence. So if you sort of had you could sort of see the whole utterance and translate it, you would get what's in the middle over here. So you would get the translation. So you can see it says 5 years ago, as a college senior, I created the video you just saw. And this is an interpreter output. So you can see that the quality is very different, and it's very bursty. So you just saw this video clip 5 years ago. There was, so this was very much talked about in Japan. I created this video as a reference for that. So you often have to, while you're listening to the source sentence being uttered, you might have to do predictions. You might have to reorder things. So if you notice, there's actually some information is actually missing in the interpreter output. The stuff about being a college senior is just not there, right? And that's because of the time pressure of producing the translation. You have to make compromises. So one thing, there was an interpreter who has about 15 years of experience, he was saying how there's often, he likes interpreting for politicians because they say the same thing sort of in a very verbose way. So they can pretty much summarize what they're saying and have a lot of time to catch up because they'll say something which sounds good to them, but the content was almost nothing. So they get a chance to catch up. So there's some interesting work on what things are harder to interpret and what things are worse. In particular, so if you think of all these different things that are happening here, you have to do some kind of segmentation to avoid a long delay in producing the translation. You want to do prediction, so a language like Japanese, which is subject, object, verb. If you kind of wait until you see the whole object, you're too late. So you often have to predict the verb and sort of make a guess at the verb and start translating the English and then catch up later on. So it's kind of an interesting thing. So they often use more vague verbs so that they are hedging their bets. They won't be wrong if they use a more general verb versus a more specific verb, right? So if anybody has any insights on sort of verbal hierarchies and stuff like that, we would love to talk to you about it. So there's been some work from Maryland on this, and there's another issue of paraphrasing. So you might want to convert the form, so it makes it easier to translate it in an online fashion, simultaneously. There's also cases of disfluencies. The interpreters often get a script. They do know what's coming. They know the topic. They know all the words that are going to come. They do some preparation. They don't just go in and start interpreting, right? So but often the people who they're interpreting for will go off script or do other things and just sort of. I have some examples, but I probably don't have time to go through it. But I'll talk a little bit about it at the end. And finally, there is a question of evaluation. It's not just about translation quality anymore. You also have this other, you have something else now. You have to produce the translation in a timely fashion. So you can't wait too long. So you'll have these two different dimensions. So I'm going to so the two bold-faced things are what I'm going to talk about. I'm not going to talk about prediction or paraphrasing. I think it's fascinating, but we haven't any results on it yet. So before I talk about segmentation, I'm going to talk about how we evaluate translation quality. And this is something called a blue score. I won't do a show of hands. I'll just tell you briefly what it is so that everybody's on the same page. So all we're doing is taking a candidate translation and matching it to a reference translation. So we want to match n-grams. So single words, how many words match, how many pairs of words match, how many triples of words match, and so on. And we just compute the precision of this. This count is clipped so that you don't sort of just produce lots of the's and get rewarded for producing the, because the is often the most frequent thing. So we want to make sure you're not gaming the metric. And you compute this precision score. So just how many n-grams did you produce that are existing in the reference translation? And then we don't want you to just produce as one word, because precision, you can game precision by just not producing too much. So if you impose a penalty for not, you have to actually translate things. You cannot just say, OK, I'm not going to translate, and I want a high blue score. So it's easier to see what this formula looks like. It's just the precision matching, and it's a weighted combination of these. And this brevity penalty just says, if your length is shorter than the reference, we're going to penalize you. So it's easier to see in the log domain. So the weights for each of these precision, so n equals 1 through n are the different n-grams. So 1 word, 2 words, 3 words, 4 words. And the weights are just set to be uniform. So it's 1/4 if you're doing 4 grams. And when I show you blue scores, I'm going to show it to you as a percentage score. So here's an example, just to give you an intuition. The blue scores here are very high because it's just comparing one sentence. Often, in reality, the blue scores are not going to be this high. So here's an input German sentence. Here's the reference translation, in case you don't speak German. And if you have a bad translation, the number of n-gram matches are going to be low, so you get a low blue score. And if your translation is better, it's not perfect, but it's pretty good, you're going to get a high blue score, right? Is that everybody clear on that? So just blue scores are a way we're going to measure translation quality, and it just gives you a number. We want higher numbers, all things being equal. So translation quality is one aspect of what we are dealing with in simultaneous translation. The other is the fact that we want to minimize delay, right? We want our translation to come out quickly. So in this case, you could just wait until the end of the sentence. You'll get a very good translation. So you get a high blue score. So you can see the German. So we're doing English to German. Most of the experiments I'll show you are English to German experiments. And so if you match the n-grams between the output here and the reference, you get a very high score, but you're waiting until the end of the sentence to produce anything. The other way the other extreme is to just do word by word. So you see a word, you translate it. You see another word, you translate it. And this will result in a translation that's not very good. So the blue score here is miserable, but it's fast because every word you listen to, you're getting a translation right away, right? So what we want is good segmentation points. So these are segmentation points which will result in a good enough translation. So it's not maybe not as good as waiting until the end of the sentence. So the blue score is not the best you can do, but it's pretty good. And you can see if you just match the output with this reference. But it's pretty reasonable accuracy in translation. And the delay is not so bad because as soon as you see I was in, you get a translation, my 20s before I, and then you get a translation. So we want some way to predict where these segments should be. So if you look at, so we want a classifier that will tell us where to segment things. But in order to train this classifier, we need annotated data. So one way you could do it is to hire a bunch of humans and say, here's where you should segment it. But it's not clear that humans are very good at this task. And so what we provide, what the first part of my talk is going to be about is providing an automatic method that will create annotated data for segmentation. Okay, so there's no humans involved. No humans were hurt in making this data. So it was just done using an algorithm. The task is English-German. And what we do in our training set is for every possible segmentation location, we translate the segments and pre-compute the blue scores, as well as later on we also use how many segments per second could you translate. So this is exponential. So there's every possible segmentation location, but we only have to do it once for the training set and save it and use this in our algorithm. So later on, even though this step is exponential, searching for the good segmentation points, we provide a better algorithm than exponential to search for the segmentation points. But we still have to spend this much time to prepare the data, as it were. So this is the example I'm going to use as my running example. This is just the source side. And below each word is a part of speech tag. So, I is a noun, am is a verb, a is a determiner, and so on. And we're going to index all of the segmentation locations with this part of speech tag pair. So for example, so if you look at, these are all the different, for this toy example, we have many different places where you can put a segmentation boundary. And we represent that with the pair of part of speech tags at that boundary, right? So in this case, you have n followed by p, and we put a boundary in the middle of it. And it occurs 6 times. So if you choose n followed by p as a segmentation boundary, it will segment it in 6 different places, okay? But so these are not used in our classifier. This is just used to index all the different segmentation positions, okay? So what we are able to do is actually, as you'll see, we will go from the one, so all of the part of speech pairs which have 1 counts, and then we'll go to the 2 counts, and we'll go to the 3 counts and do a dynamic programming algorithm, okay? So that's, I'll explain that to you in a second. So the first approach I'll talk about is this approach from the group at NARA. It's called greedy segmentation. We want to greedily maximize the sum of BLEU scores of the sentences by looking for segmentation choices, okay? And the decoding here is done sentence by sentence. And what we give as input is an average segment length, which is we'll call mu. And the total number of, from mu, we can compute the total number of expected segments, which we call k. And this is pretty easy. I'll give you an example. So the way that k is computed is just the number of the floor of the number of words divided by mu minus the number of sentences. And sentence boundaries don't count because we assume that you have sentence boundaries. We don't find segmentation points that are the sentence boundaries. So here's an example. So if you want 0, so 0 expected segments, this mu is going to be basically the length of the sentence, right? So average length of the sentence. So if the number of words here is 43, divide by 13 minus the number of sentences, you get 0. So k 0 means you have no segments. Yeah. If you have mu equals 8, so 8 is less than the length of the sentences you have. So from this, you get a k, which is the expected number of segments, is 2. You would get 2 segments anywhere in your corpus. Okay. So in this case, you have, so you notice that in this case, you have a BLEU score, which is pretty high because you're not segmenting anything. If you force it to segment in 2 places, so in this case, it chose a segment here and a segment here, which are both a noun-noun pair or part of speech tags. Your BLEU score reduces by quite a bit, right? So this is one possible way to segment it, where you have 2 segments. Another way to segment it, which is better, has a higher BLEU score, is if you segment here between a preposition and a pronoun and a adjective and a verb. So these are also 2 segments. So k is still 2, but you are doing better because it's a better segmentation. You get a better BLEU score, right? Here's another segmentation. Also, we are finding 2 places to segment. And so all that changed here was I shifted from ever. I don't know if you can see it. Can you see it? Change blindness. So you have this one over, and you get a better overall BLEU score. So in greedy segmentation, what they do is they try to find across all of these possible segment boundaries, which is the one that will give you the highest BLEU score. And that will then give you an annotated data set for a segmentation boundary. We found that this particular method tends to over-segment a small number of sentences, so it keeps a sentence which is long, so it gets a nice big BLEU score boost from one big sentence. And then it'll take one and it'll say, OK, I'm going to segment this one to death, and I'm just going to take a hit on that sentence. So we tried to get around it, and I'll talk a little bit about how we do things differently. So what we wanted to do was not just maximize the BLEU score, because that's not really the only way that we, not what we only care about, right? In simultaneous translation, we also care about how many segments per second are you producing? Are you minimizing the delay? So I'm sure most of you have heard about Pareto optimality before. It's a concept comes to us from economics, I guess. And the idea is you have multiple metrics. So in this case, you have on the x-axis the BLEU score, and on the y-axis is the segments per second. So all things being equal, you want to get somewhere here, right? You want something that's really fast and has a high BLEU score. And you have all of these different points. And this line here is called the Pareto optimality line. And the easiest way to explain this is, if you look at this point here and you look at this quadrant up here, there's nothing there. There's nothing better than it in either dimension. Whereas if you look at this point B here, you can see that in this quadrant, there's 3 points better than it in either speed, segments per second, or BLEU score. So point B is not Pareto optimal, yeah? Whereas this point on the frontier, A, is Pareto optimal. So we're going to use this concept and search for points that are Pareto optimal, ignoring all of these red points in favor of all of the blue points. Okay, that's the general idea. So we try to find the best segmentation points, take into account both BLEU and segments per second. And the input is the same. We have a desired average segment length. And for each possible segmentation location, we translate segments and pre-compute BLEU scores, just like before. The results I'm going to show you use actually this particular formulation of average of the BLEU score divided by the number of segments per sentence, which is a number that is lower than what you saw before. Since I didn't want to put two new results in this talk, so more recent work, actually, we used the whole corpus level BLEU score, and that does much better than this. This was kind of a hack, and I think we can do better than that. In fact, I think more recent results, I think if you just use a corpus level BLEU score, it does better. And then we also compute the segments per second. So this is the same idea as before, except now you have two different criteria. One is like how much better are you doing at the BLEU score, the translation quality, and how much faster can you translate because you have this segment. So one problem with the greedy segmentation is if you let it, it will just take longer and longer segments because it's greedily trying to maximize the BLEU score. In general, longer segments will give you better BLEU scores. But that's not always the case, but in general, that's true. So what we wanted was something that can balance the BLEU score with the segments per second. So I'm going to give you an example of finding two segments. So basically, we're going to focus on just this part of this table. So if you look at, and we're going to use a dynamic programming algorithm. So we compute first all of the segments, basically all of the single segment boundaries. And then we use the single segment boundaries to produce pairs, so two segment boundaries, and so on. Okay. So some of them, if you want two segment boundaries, you can just pick NN. and that will give you it has a frequency of 2, so you already got 2 segments. Or you could pick PS, which is a frequency of 1, and SN, which has a frequency of 1. So you could pick 2 of those and get 2 segments, right? So you can get 1 plus 1, or you can get 2 directly, and so on. So when we go up to 3, you get all of the different combinations. Okay, so let me show you. So these are the 2 different options. So this one has occurs twice, so you get 2 segments, or you have this and this, so you have a 1 count part of speech tag pair, and another 1 count, and so you get 2 segments. Okay, so here's what it looks like in this example. That point over here is the one with no segments, so just the sentence boundaries. And then let's say you pick all of the segments with a frequency 1. So that's PS, that's SN, that's AV, that's NA, and that's all of them, right? So if you look at what's on the Pareto frontier, those 2 points, right? So you can see that we can ignore these 2 because they're not better either in speed or BLEU score, so we can just forget about them. Now we start with 2 segments. So we can start with NN, which occurs twice. So NN occurs over there, so it's pretty bad in the BLEU score, right? You don't want to split in the middle of a noun phrase. You get bad translations. You get PN, which occurs once, and PN occurs twice as well. And so here you have these 2 for 2 segments. And this is the best in the features happening twice. But you also want to consider 2 segment boundaries that occur 1 each. So you have PS and NA that occurs there, and PS and AV occurs there, PS and SN occurs there. So if you look at all of the 2 segment cases, we have this guy. So one thing we do right now is, of all of the 1 segment cases and the 2 segment cases, we keep the one with the highest BLEU score, and that's just because otherwise we get far too many candidates. We are looking into just keeping the entire Pareto frontier, but right now it just produces way too many candidates. So we're trying to find a way around it. But for now, what we do is we pick one. This one is the one of all of the different Pareto frontier points, the one that has the highest BLEU score. Okay, so this is basically our algorithm. I'm not going to show you the pseudocode of the algorithm. I hope you got the insight into our dynamic programming algorithm from the example. If you're interested, I'm happy to show you the pseudocode, and we can talk about it. But hopefully you got the idea. So in order to evaluate our segmentation annotation, what we did was used this IWSLT data for training. So that's our training set is what we maximize the Pareto frontier over. And then we also run the same segmenter over test data that we haven't seen before. And we compared a few different segmenters. There was the state-of-the-art heuristic speech segmenter, which basically predicts commas and then segments in those places. The greedy segmentation approach I showed you, and our Pareto optimal approach. And this is what we see. So you can see that this curve over here is our Pareto optimal segmenter. It's kind of pushing the knee of the curve, right? So this is the greedy segmenter here. And these are the different mu values. So mu, if you recall, is the average segment length. So if you get a large segment length, obviously you're going to get a better BLEU score on average. So you get better BLEU scores here. This is a mu equals 2, so this is more like the word-by-word translation system, right? It's very fast, but it gets a very bad BLEU score. But what's interesting about showing it in this way is that you might actually make a trade-off. So the system, when it's doing translation, might want to make a trade-off. If you're running behind in your translation, you might want to be more aggressive about segmentation. If you are, you're not in time pressure at this particular moment, you can wait and do a better translation, right? So, yeah.
Question. So it looks like you're doing all this from text, but
Yeah.
you have segments per second. How are you getting the time? And if you are using speech, are you using that in the comma segmenter?
Yeah, so for these results, we are not using the time taken to produce the translation. We are doing it now. I don't have the numbers to show you, but we are running experiments where we use SayIt, Hal Dame's tool, which will take a piece of text and then tell you how much time it takes to say it. So right now, what we are calculating is segments per second is just how much time did it take to produce a translation, just the translation time.
On the computer?
Yeah. So shorter segments are faster. Like if you don't wait until the end of the even if you partition it into smaller segments and you add up all of the times, it's faster, right? Because the number of hypotheses are smaller when you have a smaller segment. So I should have repeated your question, but I'll do it next time. So even if you pick a single point, so let's say you pick mu equals 3 or mu equals 8, you can compare these two segmenters. So what we want to do is to do pretty much the same in terms of BLEU score, but get faster, right? So because we're paying attention to these two things, and the greedy segmenter isn't. So we can see that in these results. So that's exactly what we see. We get faster, more segments per second. We maintain the same BLEU score. So the next step is to take this training data and build a classifier. So this is another baseline segmentation classifier one can build. Basically, if you look at a alignment matrix between a German sentence and an English sentence, you can see that there are places where there's not much reordering. And so you can have a heuristic that says, prefer these monotone phrases of a certain length. So you still need to say like mu equals 5, otherwise you'll just pick word by word, right? And so these boundaries are then taken to be annotation decisions for a segment. So basically this requires parallel data, but it's fairly easy to come by. So we created the training data using the Pareto optimal search, and then we used it to build a segment classifier. I won't go into a lot of detail about the features, but basically we used a lot of different features that we had actually used before in a paper. We explored more features than this in a previous paper, and these are the ones that worked for us before, and so that's what we used. The only thing, I guess, that needs more explanation is the reordering feature. So we have the last word of the segment. So this is the segment from our scientists and engineers. And this is the proposed segment boundary. And we also look at the next word, the word after the segment boundary. So we have one word of look ahead to decide the segment. And we have the last word, which is engineers, the position and the length. Because if your segments are getting too long, then probably you need to add a segment boundary. We also have part of speech n-grams of the segment. We also have the cross-segment part of speech tag. So engineers is a plural noun, NNS, and IN is a preposition. So this pair represents the part of speech tags here. And reordering is actually a feature we took from. So this assumes some knowledge of machine translation innards. So I'll go fast. If you don't understand this part, it's perfectly fine. You don't need to. These are actually lexicalized, the monotone lexicalized reordering feature out of a phrase-based system. And we take basically this pair of numbers is how likely is it to be a monotone phrase, right? So at the beginning of the segment and at the end of the segment. Like I said, if you didn't understand that, that's fine. These are all the features. And this is all of this. So this is set 1, set 2, set 3, set 4. And you can see that the reordering features don't work all that well. The PO segments seem to be performing pretty well. You get astonishingly high recall in this particular setting of features, which is quite good. And the data was from IWSLT. OK, so far, I've shown you how to create annotated data for segmentation, how to create a classifier from the annotated data. And now we actually want to do translation with segmentation, right? So we want to build a machine translation system that does what a human interpreter does. So just a brief overview, if you haven't sort of seen how statistical machine translation systems work before, we rely on large quantities of translation data, and then we learn from this translation data in order to, we call it parallel data. And it's widely available. You can crawl the web for parallel data. You can look at United Nations documents, European or Canadian Parliament documents. There's Wikipedia in different languages. So you often find parallel data out there in the wild. And we want to use it to build a translation system. So I'll show you a few details about our translation system. And this is kind of what Mariam has been working on for her PhD, is building a decoder for a left-to-right decoder that is aware of hierarchical reordering. So let me explain that. So here's what we do first here's a fragment of the parallel text. So there's English and there's German. And what we learn alignments from these parallel texts. And so these alignments tell you that world is translated as Welt in German, right? The next step what we do is we extract these weighted translation rules. So in many cases, they are just phrases. So that this word in German translates to this phrase in English. And there's a weight associated with each of these translation rules. You can think of it as a bunch of feature functions, just like in a standard machine learning framework, and weights for those features. That gives you a weight for that rule, right? And you can also do other interesting things like that there is an x1 before the world and an x2 after the world. And when you produce the translation in German, you should take this x1 phrase and put it here, and this x2 phrase and put it here. Yeah? So it sort of captures some notion of the reordering. And finally, we try to find, so this, you can think of this as a derivation. So this D is a derivation which takes this English and produces this German. And what we want to find in general is the argmax derivation that has the most the most likely rules. So this is what we call a decoder. So the decoder takes as input the source language sentence and produces the most likely target language sentence, right? And this is a sort of fairly common structured prediction task, right? So you want to find the argmax. You also need to learn these weights. So you need to learn the weights and then also have an algorithm to compute this argmax. So the obvious thing to do is to enumerate each derivation. So you just say, let's just go through each of the derivation and find the one that's argmax. That, unfortunately, is exponential. The most common way to deal with this is to make a dynamic programming algorithm, which is CKY, if you've heard of that. And our algorithm is an early style decoder, which actually takes n squared b time. And our decoder is available on GitHub here. It's not always updated. So if you notice something is missing, just please email me and we'll push it. It's grad student code. It's not like production quality. Yeah. So I'm going to show you how we integrate this classifier. I'm just going to go very briefly and describe how it works. Actually, I'm going to skip this. So what we first do is the input to the decoder is the first segment. So this asterisk over here represents the first segment. And in order to determine the segment boundary, we need to have one word of look ahead, right? And so what we do is we create this hypothesis. We're going to cover this entire segment, so from 0 to 4. That's what represented here. And then we're going to explore one of the rules. So I'm just showing you one possible way to search for the hypothesis. There's going to be many, exponentially many. And we're going to explore it using this dynamic programming algorithm, right? So we is going to be the first word. We translate it. And it's going to then produce a goal of parsing, decoding the rest of it, 1 to 4. And notice that we need, in this case, we can do reordering because we have the entire segment, right? So we are always producing the translation from left to right on the target side. And the reason to do that is that we actually can reduce the number of language model calls substantially by going left to right on the target side. Okay, so that's then the next step. So the interesting thing here is this rule is this translation rule says x1 need x2. And in German, there would be x1, x2. So what we do is we're going to first find a translation for desperately, right? And then find a translation for great communication. Yeah. So all of this reordering is handled by these weighted rules. Yeah. And then we have desperately that, as I said, and then we have great communication. And now we've reached a segment boundary, so we emit the translation, right? And now I can go a bit faster because we go to the next segment from our scientists and engineers. And we get a phrasal translation from our is translated as a group. And then you have scientists and engineers also translated. We emit that translation, and then we go to the last segment in order to change the world. So the whole sentence is, we desperately need great communication from our scientists and engineers in order to change the world. So I feel like I'm not living up to it. We'll see. So here's how we evaluate it. We built an MT system. All of these details are not really important. I guess we do have a lot of data to train the system. All of the translation rules comes from a large amount of data, not just a small data set that we had before. And then we have the segmenter trained and using the classifiers. So the classifier is being incorporated into the decoder. The decoder at every word is calling the classifier and asking it whether there's a segment or not, right? That was in that animation I skipped for reasons of time. So here's our evaluation results. And you can see the prosodic segmenter here. It seems to have a pretty good blue score. It doesn't segment that aggressively. So it has fewer number of segments. The PO set 3, these actually, so This was the one that obtained the best classification accuracy back in that section where we were evaluating the classifier. Also seems to do a good job of balancing the BLEU score and the number of segments. So basically, the segments per second is pretty high. So that's 3.73. And the alignment heuristic, which was the other classifier we built, is actually worse in both segments per second and BLEU score. I didn't show you all the other alignment results. Just take my word for it. They were worse than align set 4. Otherwise, the slide was too busy. So this basically is our eventual validation of the Pareto optimal approach. Is it actually can be used to build a classifier, which then can be incorporated into a decoder, and then it can produce timely translations. So we used this dynamic programming algorithm to annotate data. I showed you a multimetric optimization algorithm over both speed and accuracy. And we provide this sort of trade-off choice between speed and latency and translation quality. And we incorporated it into a decoder that produces incrementally, so it sort of takes a stream of words and then chooses where to segment using the segmentation classifier and produces the translation. So what we aim to do is we've actually already doing this. We have some preliminary numbers, but not all the numbers. We have better ways to compute the scores for translation quality. Like I mentioned, doing corpus level BLEU helps. For latency, we are, as Mari's question was about incorporating the actual time it takes to say the translation, we actually added that too. And we have the annotation. I got an email at 2 a.m. last night that it's in fact ready for the decoder algorithms to work, so we'll see how it works. We really like to, we made this assumption for reasons of computational efficiency, is to pick only 1 point from the Pareto optimal frontier for each step in the dynamic programming algorithm. We want to relax that. And I'm excited about this is we have some, right now when we're computing BLEU scores, we're computing against reference translations that were actually, they looked at the whole sentence. So what we want to do is actually compare against human interpreter output, because that's a more realistic output to compare against, because they're doing segment by segment, we assume. We don't know what's going on in their heads, but we assume they're doing segment by segment. So, and finally, I'm very excited by this, is to somehow try to use the Pareto optimal point. So train many different classifiers all across the curve. And then depending on whether the decoder feels there's time pressure, to switch between the classifiers as it goes through the sentence. That's easy to say, but Mariam that kind of was like, sure, you can say that, but somebody has to implement it. So finally, I'll leave you with a quote from Stalin. So I think so if a person like Stalin feels out of control, we hope to take simultaneous translation and just not be just something that's exclusive for just a few people, but everybody should have access to simultaneous translation. Right now, that's not possible because you need these sort of basically professional athletes who are the interpreters. If you have machines that do it, everybody can have simultaneous translation. Thank you.
Thanks, Anoop. We have time for a few questions.
No?
So if I understand correctly, the hypothesis space you're searching when you do the initial segmentation is based on selecting pairs of part-of-speech tags, and then that's a rule, and you say, every time I see this pair, I'm going to split in the middle. In your slides, the part-of-speech tags you showed looked like really coarse versions of the Penn Treebank tags. I'm wondering, did you actually use Penn Treebank tags? Did you use something else?
We use Penn Treebank tags. Yeah.
So if you coarsened them, it might make a difference.
Yeah. Yeah, we tried a few different things. We tried just words. We tried, I can't remember now if we tried coarse. We tried some other ways to basically partition the segments that didn't use part-of-speech tags. But you're right, we should try to use coarse ones and see.
Maybe also like brown clusters.
Right.
And another thought is that you could look at the part-of-speech, but you could also look at the pair. You could widen the scope. You could also parse the sentence and look for sort of tree features.
Yeah.
Do you think this is like I guess in my head I'm imagining that interpreters actually have sort of linguistic criteria they use to decide where to break, and they're probably not part-of-speech bigrams.
Right. Yeah. So to some extent, we are relying on the part-of-speech bigrams to make our dynamic programming algorithm work.
Yeah.
So it's not the case. It's actually looking at every possible segment boundary, right? It's just collecting them in terms of part-of-speech bigrams. So it's.
But you make a decision about the collection that share the same part-of-speech.
Yeah.
Right? You're lumping them together, so you're designing a hypothesis.
Right. So it's not surprising that a classifier that uses part-of-speech bigrams kind of does better. But yeah, you're right. So you could do a lot more complicated things. You want to be careful that you don't have it destroy this. So you want to collect things and sort of say that they're common somehow. If every segment point is unique, then you kind of don't get the benefit of dynamic programming.
If I understand right, every iteration of this thing, you have to train an MT system and evaluate a BLEU score.
We actually pre-compute for all the segments. And so every possible segment boundary, we've pre-computed the translation and the translation score and the time taken for each segment. Yeah. It takes a while. Yeah, Murray.
So I'm curious about the baseline. In the end, you called it a prosody predictor, and earlier you called it a comma predictor. Is it actually, because those would be two different things in my mind.
Yeah. Yeah, sorry. It's the same one.
So it's relevant because it turns out that part-of-speech bigrams are in fact fairly powerful at predicting prosody. So to some extent, that's what you're
Right.
doing.
Right.
And so I'm just curious: is the target actually commas, or is it based on?
No, I wrote prosodic, but I meant it was the same thing as before. It's a Sridhar comma predictor. Yeah.
Okay, so you're probably doing more prosody prediction than they are.
Possibly. Yeah. Yeah. I hope so.
I'd love to talk to you more about that.
Yeah, thanks.
So I have also one question. So you said you are working on improving the quality of the translation. So do you think you can do the segmentation and translation jointly? Like this segmentation can be a latent kind of space to do a better job on translation.
Yeah, I think what I mentioned was just in terms of measuring the translation quality score better, because there's different ways to do it. Like we had this particular, I'll call it a hack, where you take the average over the BLEU scores per segment. And yeah, so I think it's definitely better to just take the corpus level BLEU score. That's what I meant. But yeah, if you sort of jointly do it, I think it just, it's already hard, so this would make it much harder. Yeah, I think it's probably computationally infeasible, but yeah. Maybe if you have some kind of low dimensional stuff, maybe it'll work, yeah.
And do you know, did human interpreters go towards shorter segments or longer? Did you guys do any study on that?
So the thing is that you don't hear, you don't explicitly see the segments, right? So I've heard a few of these, several of these now, and there's an initial thing where they don't obviously start translating right away, so they wait. And then they're just talking. Some translators will just keep talking. They don't pause. Some translators will pause. Some translators just sometimes ignore stuff and just sort of go from the script. You get all kinds of things. So the EPIC corpus is a collection of human interpreter data from the European Parliament. It's freely available. They also have videos of the people talking in the European Parliament and the translations, interpreter output. So they have speech files, they have transcripts, they have everything. It's really good resource. It took a lot of time and money to collect that corpus, and we are just starting to use it in our work now.
Great. Any other questions? Great. Let's thank Anoop again for his interesting.
Thank you.